Hello and welcome. This video is part of a series exploring statistical techniques and methods in kinesiology. Specifically, we will be exploring the one-sample t-test, also known as the one-sample student's t-test. To begin, let's cover the basic setup for this analysis. Our data are body fat percentage measurements using dual energy X-ray absorptiometry or DEXA among a sample of young adults aged 20 to 25 years. Our total sample size is 50, and these data are synthetic in nature. That means these data do not come from actual participants, but were instead created artificially, what we refer to as synthetic or simulated data. In this case, our research question asks whether mean body fat percentage among our sample significantly differs from the known population mean body fat percentage among U.S. adults aged 20 years and older. For this analysis, let's assume that the mean population body fat percentage is 33.9%. Within a null hypothesis significance testing framework, our null hypothesis is that mean DEXA measured body fat percentage among our sample of 20 to 25-year-olds does not significantly differ from the known population mean body fat percentage of 33.9%. Our alternative hypothesis is that mean DEXA measured body fat percentage among our sample of 20 to 25-year-olds does significantly differ from the known population mean body fat percentage of 33.9%. Before beginning the analysis, let's briefly review the assumptions associated with this test. 1. The sample data we analyze should be continuous in nature. That is, the data should not be drawn from a discrete distribution. 2. Each observation within the sample should be independent of every other observation. 3. Our sample data should be drawn randomly from the underlying population, that is, random sampling. And 4. Sample data should be drawn from an underlying population that is approximately normally distributed. Let's now perform a one-sample t-test with the synthetic data in our example using R. To begin with our one-sample t-test using R running within our studio, we need to point to the data's location using the setWD function and read in the data using the read.csv function. We assign the data to a data frame object named DAT and quickly inspect this data frame by entering in head.dat to the console, which will print the first 6 observations to the console. We see that we have a single variable in the data frame named BF_pers representing percentage body fat. We then can briefly calculate descriptives such as the mean and standard deviation of the BF_pers variable, which has a mean of 27.1% and a standard deviation of 9.7%, as printed in the console. Before performing the one-sample t-test, we can explore R's generic t-test function called t.test by typing in a question mark followed by t-test into the console. You should now see the student's t-test function described in the help pane in the lower right corner of RStudio's display. In our case here, we will not use many of the expressions contained within the t-test function. We can leave alternative unchanged as it assumes a two-sided test by default. However, we ultimately will specify a mu value different from the default of 0. Now for the actual one-sample t-test. We use the t.test function, specify that the vector x is equal to our percent body fat variable, dat, $BF_pers, and then we additionally specify that we want to test the mean of our sample data against the known population mean mu of 33.9. After running the t-test, we see the output within the console. Printed results give us a calculated t-value, degrees of freedom, and observed p-value. The printed results also give us a calculated 95% confidence interval and the calculated sample mean. In our case, the t-value is -4.96. Degrees of freedom are equal to 49. And the observed p-value is 8.79 times 10 to the -6th power. We can also perform some assumption checking relevant to data normality by creating some graphics. The first one we can look at is a histogram of body fat percentage data with a normal curve superimposed on top of the histogram. We can also use other graphical techniques to inspect normality, such as a QQ plot, which we will create next. And lastly, we can use formal statistical tests, such as the Shapiro-Wilk test, to evaluate data normality. To do this, we use the Shapiro.test function with our target variable $BF% contained within that function. Let's now perform another one-sample t-test using the same synthetic data, this time using JASP. To perform the one-sample t-test in JASP, we will first read in the data by going to the Open tab and then navigating to the location on the computer where the data exists. We will then select it and click Open. Now we have a single variable read in, BF_, or body fat percentage, and then we will navigate to the t-test dropdown, where we're given options for both classical and Bayesian t-tests. In this case, we will stick with the one-sample t-test of the classical nature. Here we will take the BF_, variable, move it over to variables, ensure student is checked under tests, and change the test value to 33.9, the population mean against we want to test. We will then check boxes for location estimate, effect size, descriptives, and normality and QQ plot under assumption checks. We have the one sample t-test results at our right with a t-statistic, degrees of freedom, and p-value represented, as well as an effect size estimate and a standard error associated with that. We have the Shapiro-Wilk test as a formal statistical test to evaluate normality. And then we also have a QQ plot of the variable to test normality graphically. Lastly, there are some descriptive statistics presented at the bottom of the results here, giving us our mean, standard deviation, standard error, and coefficient of variation. Let's now interpret the output of our statistical analysis. As a reminder, the question we are asking in this specific example is whether our sample mean significantly differs from the known population mean body fat percentage of 33.9%. In this case, our sample mean of 27.1% seems quite a bit lower, nearly 7% lower than the known population mean. Examining our output, we see that our observed t-statistic is negative 4.96, and when we evaluate that at n-1 degrees of freedom, which is 49 degrees of freedom here, we observe a p-value of 8.79 times 10 to the negative 6th power. Since our observed p-value is less than 0.05, we conclude that these results are significant. Before formalizing our interpretation of these results in the context of our hypotheses, let's check our assumptions. In this example, we accepted from the outset that we were working with continuous data, that observations were independent of each other, and that our data were obtained using random sampling. The last assumption we need to check is whether our data were drawn from a normally distributed population. There are a number of ways to evaluate this assumption. The first we will explore is by examining a histogram of the sample data. Here I have imposed a normal curve over the top of the distribution, and although we do not see a perfect distributional shape of the vertical columns matching the normal curve, we do not see any dramatic skewing one way or the other, or any notable ridges in the data's distribution. Evaluating normality further, we can construct a quantile-quantile or QQ plot. In this example, we want to see whether or not most of the observations line up along the red dashed diagonal. In general, the data here are lining up quite nicely along that diagonal, suggesting that the data are likely normally distributed. Lastly, we can use a formal statistical test, such as the Shapiro-Wilk test, to evaluate normality. The observed p-value here of 0.8305 from the Shapiro-Wilk test is quite high, and because that p-value is greater than 0.05, the results from this test suggest that there is a lack of evidence these data are non-normal. If we observed a p-value less than 0.05, that would serve as evidence that these data violate normality. That said, formal statistical tests of normality, like the Shapiro-Wilk test, are highly sensitive to sample size, whereby even extremely small deviations from normality among large samples will cause this test to demonstrate a significant result. therefore suggesting the data are non-normal, when in reality the data likely are sufficiently normal for our purposes. Because of this, it is more common to evaluate normality using graphical techniques alone, such as the histogram and/or QQ plot methods that we just covered. Moving on to the final evaluation of our hypotheses. Because we observed a significant p-value for the one-sample t-test, less than 0.05, associated with our mean body fat percentage value that was nearly 7% lower than the known population mean body fat percentage of 33.9%, we reject the null hypothesis. We would then state that there is sufficient evidence to conclude that mean DEXA measured body fat percentage among our sample of 20 to 25-year-olds significantly differs from the known population mean body fat percentage of 33.9%. That concludes this video describing the one-sample t-test with examples in R and JASP.